All right, I want to talk a little bit about which equations we can use the separation technique on. And here's an example of a differential equation again, dy dx equals 2y plus 5x. So what can we do with this? Well, we want to get the, we want to get all the y on one side, all the x stuff on the other side. So we start by, I don't know, maybe we start by getting rid of the 2y. So we get dy dx minus 2y equals 5x. All right, then we try maybe multiplying by dx. So over here, we're good. We got 5x dx. And over here, these cancel out, so we get dy minus, oh, wait, 2y dx. So now we've got the dx here, and we got to get we need this dx to be on the other side, right? But, okay, so long story short, this isn't going to work, okay? And the reason this isn't going to work is because separation, the separation of variables technique, only works on separable equations. And what is a separable differential equation? Well, in effect, it's something that looks like this, where you've got your derivative. It's something that, well, at least could be written like this. You've got your derivative of f of x, f prime of x, is equal to some function of x times the function f of y. Another way to think of it is g of x, this plus f of y times f prime of x equals 0. That those are equivalent, I'll leave to you to figure out. But either way, what we need is an equation of x and an equation of y that we can kind of pull apart, that we can separate, so that we've got dy dx over here, right, is g of x times f of y, and we can separate them and bring the dx over here and the function of y over here, so that we get f, or 1 over f of y dy equals g of x dx, and then we can do this thing that we've done where we take the antiderivative of both sides and go ahead and solve from there. So what we need is to have, again, a separable function. I'm going to go and show you one more. I'm going to do one example here too. So I'm going to do one example of solving. It's a little bit different. Okay, so this one, I've got two functions on this side, and you can check it out, right? I've got two functions here. I've got this function on top, which would be like, my g of x, and I've got another function over here, 1 over f of x, or 1 over f of y, but this is my f of y function is going to be, 1 over 2y plus cosine y, and then this is just becomes g of x times f of y. All right, that's kind of unnecessary, just to check, but let's try it out then. Okay, again, we'll rewrite this with the Leibniz notation, dy dx, 6x squared over 2y plus cosine y. And there's a reason I want to look at this one specifically. We'll see in a second. Multiply by dx on both sides, and we get dy equals 6x squared dx over 2y plus cosine y. And then we'll multiply both sides by 2y plus cosine y equals 6x squared dx. All right. Now, from here, we do our antiderivative of both sides. All right. This, on the left-hand side, is pretty straightforward. Derivative of 2y, antiderivative of 2y is just going to be y squared. The antiderivative of cosine y is just going to be sine y. And that's going to equal 2x cubed plus c. Remember, we only need c on one side. Now, in terms of, on the other ones, we've gone to this, the next step, which would be to make it an explicit function of y equals something, something, something. But we're not going to be able to do that here. There's going to be no way for us to get y by itself. So we have to leave it like this, and that's okay. We have an implicit function, or a function that's implicitly defined, and we just leave it like that. But that's going to be our answer. That's all we can do. Okay, that's it.